Assalamu alaikum. Today we'll start talking about chapter 22, which is about filters. And in this chapter, we will concentrate about two type of filter, which is RC low pass filter and RC high pass filter, section 22.5 and section 22.6. We can define a filter as any combination of passive or active element designed to select or reject band of frequencies is called filter. If you design any circuit to pass some frequency only, this is called filter. We have two type of filter, one type called passive filter and other called active filter. The passive filter are those filter composed of series or parallel combination of RLC elements, and the active filter are the filter that employ active device such as transistor, operational amplifier in combination with R, L and C elements. But in this book we will concentrate about passive filter because this we will study two type of passive filter also. There are four type, but we will study as mentioned here RC low pass filter and RC high pass filter. We have said four type: low pass, high pass, band pass and band stop. You can see this in next page, the difference between each type. Low pass, it will allow frequency from 0 to cutoff frequency. Okay, this is called cutoff frequency. And high pass, it will allow the frequency from cutoff frequency and more. For band pass, it will allow the frequency from F1 until F2 only, and other will reject. For band stop filter, it will allow from 0 to F1 and from F2 and more. Now let us talk about RC low pass filter. RC low pass filter, sorry, back to, we have this circuit. It is called RC low pass filter. RC we can design by RC low pass filter and high pass filter. If we design a resistor in this side and capacitor in this side, it will called low pass filter. If we interchange the resistor and capacitor, the resistor become here and the capacitor become here, it will called high pass filter, RC high pass filter, which is next section. To see the behavior of this circuit, we can see the capacitor if we substitute the frequency and the reactance 0 or high frequency. You can see here the xc equal 1 over 2 by fc. If we substitute the frequency by 0, you will get infinity. Infinity mean open circuit, okay, which will means V input equal V output. If you put 0 frequency in this point, you will get Vi equal V output. But what about if we substitute frequency as high frequency? You will get almost almost zero, because here and this side will be as short circuit. Then vi equal v out equal 0. Okay, and we can draw v out versus frequency of low pass RC filter by this, and 0 you will get vi v input, the v output will equal v input, and then until we reach some point it will decrease when we increase the frequency until we reach almost 0. And this the figure we can normalize it by divide v output divide by v input, only to see the figure by this number as a percentage. You can say normalization, it is a process whereby a quantity such as a voltage, current, or impedance is divided by the quantity of the same unit for measure to establish a dimensionless level of a specific value or range. In this figure, it is similar to this figure 22.13, 22.14. This is the same, but in 22.14 we divide V output over V input, and we get it. If we in zero frequency, you will get 1 as 100%, and it will decrease as we said, and in cutoff frequency you will get 70.7% or 0.707. Now, if we need to find the value of V out from the input, V input, okay, we can follow the driving equation. It is V out by voltage divider rule. You can say XC multiply by VI, and then divide by the combination of the impedances. Okay, if we normalize this equation by dividing V out over V input, you will get this equation, and here we can write the magnitude alone and in phasor form or polar form, and the angle in this shape. Okay, if you remember, we studied this in chapter 15 and 16 when we studied series and parallel circuit. Okay, now if we divide the angle minus 90 divided by minus tan inverse xc over r, okay, you will get minus 90 plus tan inverse xc over r. For the magnitude alone, this is the value xc over root of r square plus xc square. If we divide by xc all the terms, you will get 1 over root r over xc all square plus 1. And for the angle, theta equal minus 90 plus tan inverse xc over r, which is by math properties, you can write it minus tan inverse r over xc. Now, for special case, if we put xc equal r and we substitute here, you will get r equal xc, you will get 1 here. Okay, and 1 plus 1, 2. 1 over root 2, it is 0.707, which we mentioned before. This means if we say the impedance equal resistor, impedance for the capacitor equal resistor, okay, we can find the value of cutoff frequency. It is called cutoff frequency or critical frequency. Okay, we replace FC replaced by R, and R become numerator. 1 over 2 pi RC. This is how to find the value of cutoff frequency. Now, if we assume V input with V input to the angle 0, okay, then you will find the V input here with angle 0. You can divide and find the final answer here. Xc multiplied by Vi divided by root r square plus xc square, and the angle theta. The angle theta is the angle between the Vi and V out. And we know that theta, it is minus tan inverse of r over x, which is always negative. This means if this quantity will be with angle negative and our input with 0 angle, okay, this means will be always output lag V input, okay. Now if we need to see the frequency with the angle, how to draw the frequency with the angle, assume we substitute xc with very small quantity of xc, you will get r over xc is large quantity, okay, resulting in minus tan inverse approach almost minus 90, okay. In the opposite, if we put xc in large quantity, you will get very small r over xc, and now if you substitute minus tan inverse r over xc, you will reach 0, which in this point. What about if we substitute xc over x over r? This means tan inverse 1, and we know that tan inverse for 1 it is 45, and because minus here it's minus 45, okay. This means the angle in the cutoff frequency will be minus 45, and because we know that it is V out lag with the V input, okay, we can opposite the sign for the angle 0, 45, 90, and we notice that in low pass filter, okay, the frequency cutoff with the angle always we will get the answer, the angle less than 45, okay. You can see here the summary, the cutoff frequency equal what, and if the frequency less than cutoff, the value of output more than 0.707 of input, and if the frequency less than cutoff frequency, you will get output less than 0.707 V input, and we know that V output lags Vi by 45 degree at cutoff frequency. For low pass filter, we can use RL combination, but you can see here in this figure RL combination, but in general RC combination is more popular due to the smaller size of capacitive element and non-linearization associated. Okay, we prefer to use RC combination better than RL combination. Now let us see example 22.5. We have circuit 22.18. We have voltage input, resistor, and capacitor. Part A, sketch the output voltage V out versus the frequency of the low pass RC filter on figure 22.18. We know that this is the shape for the low pass filter, okay, but we need to determine the cutoff frequency and other value. Okay, cutoff frequency, we know that it is 1 over 2 by RC, and we have the resistor and we have the value of the capacitor. You will get the cutoff frequency. It is 318 kilohertz. We can write it is 318. And we need to find the value of voltage and cutoff frequency. We know that we need to multiply the V input, which is 20, multiply by 0.707, you will get 14.14. Okay, this is the main point in low pass filter, RC low pass filter, as we studied now. Part B, determine the voltage V out at frequency 100 kilohertz and 1 megahertz, and compare the result to the results obtained from curve in part A. We notice that 100 kilohertz less than cutoff frequency, and 1 megahertz is more than cutoff frequency. Okay, if you substitute, we know that the magnitude for V out, it is V input divided by R over X all square plus 1, but we need to find XC now. Okay, after we change the frequency, you can find XC by this formula. You will get 3.18 kilo ohm. If you substitute in this formula, you will get the value of the voltage input 19.08. Okay, 19.08. This is at 100 kilohertz. What about 1 megahertz? You need to calculate XC. You will get 0.32 kilo ohm, and V out you will get 6.1, and at 1 megahertz you will get 6.1 volt. Part C, sketch normalized gain V out over V input. It is similar to this, but we need to divide each value of voltage by 20. You will get this shape. It's 0.9 20 input to become 1, and here the value of 100 kilohertz become 9.954, and cut frequency will be 0.707 voltage, or sorry, normalized, and 1 megahertz become 0.305. For section 22.6, it is RC high pass filter, and we mentioned before if we interchange the resistor and capacitor from low pass filter, you will get the circuit for high pass filter. Now, if we have very high frequency, you will get reactance of capacitor. Capacitor is very small, and we can draw it as a short circuit, as mentioned here in 22.2. This means at high frequency you will get V input equal V output. Okay, you can see the draw here. For high frequency, V input equal V output. What about the frequency 0? You will get the reactance of capacitors quite high. and we can draw it as open circuit. This means V output equal 0, because this is 0 frequency, you will get 0 voltage output. Now if we need to drive the equation, we can say by voltage divider rule, R multiplied by V input divided by R minus JXC. And we know that the magnitude for the numerator, it is root R square plus XC square, and the angle minus tan inverse XC over R. To normalize, we divide V output over Vi input, because we need to normalize this equation. And the equation for the formula for the normalized result, it is R over root R square plus XC square. If we divide by R, we will get what? 1 over root 1 plus XC over R square. It is opposite from the low pass filter. For tan inverse, the theta equal tan inverse XC over R. Now, for special case XC equal R, which is critical frequency or cutoff frequency, we will get the same thing, 0.707. And to find the cutoff frequency, it's the same formula, 1 over 2 pi RC. If we need to now to draw the phase angle response for the high pass RC filter, we need to concentrate on this formula, tan inverse XC over R. For high frequency, what you will get? High frequency, you will get low value of XC, almost 0. This means tan inverse almost 0 equal 0. You can see here, it is in high frequency, you will get 0. And what about if we have 0 frequency? You will get high value of XC. If we have high value of XC, tan inverse high value, the theta will be 90. Okay, if anyone asks you to draw the phase angle response of high pass RC filter, you can draw this. And we know that if we make RC equal R equal XC, you will get tan inverse 1, which is 45. Cut frequency, you will get angle with 45. In this circuit, the V output lead V input. Okay, since the angle theta is angle which V output lead V input throughout the frequency range. Okay, high pass filter RC filter is referred to leading network, and this is the summary for high pass filter. It is almost similar to low pass filter, but with some change, with some opposite formula. Okay, now let us start with the example 22.6. Give you R equal 20 kilo ohm and C equal 1200 picofarad. First question, first part, sketch the normalized plot of if the filter is used as both high pass and low pass. Okay, first we need to find the cutoff frequency. similar. It's got formula for high pass or low pass. You will get 6631 hertz. This is cutoff frequency. And if we need to draw, no need to calculate because he asked normalized. We can write 1 for high voltage and 0.707 for cutoff frequency, and draw the shape of the curve in low pass filter and the shape for high pass filter starting from cutoff frequency. Part B, he said sketch the phase plot for both filter in part A. Phase plot, okay. We know that the low pass filter starts from 0 until cutoff frequency and then increase until 90. And for high pass filter, it starts from 90 with 0 frequency and decreased until we reach the cutoff frequency with 45 degree and then decreased until we reach 0. Part C say determine the magnitude and phase of V output of over V input at frequency half of cutoff frequency. What does mean for only for high pass filter? What does mean cutoff frequency divided by 2? This means 6631 divided by 2. You will get 3315. Now by opposite, you can substitute the frequency in this formula because we have the value of capacitance. You will get the capacitor, which is 40 kilo ohm. Now we can substitute in the formula. You will get the value. It is 0.4472 normalized value. Normalized value, because in this example it is not given the value of the input voltage. It will always ask you about normalized value. No need to get input value if he is asking about normalized value. I mean, no need to get voltage value input. Now for theta, it is time inverse xc over r, and we know the value of r, and xc 40, we get it 40. You will get 63. Then the value of the normalized 0.447 angle 63.43. If we have the value of input, you can find the value exactly of the output voltage by multiplying the input by 0.447. By this example, we end with this chapter. Thank you for your listening.